Alright, so what I wanted to show you here is sort of now that we're talking about two-dimensional motion, you have a horizontal velocity. It's helpful to talk about horizontal and vertical. So these two velocities together are vectors. I'm going to call this my beginning velocity in the horizontal x direction, and I'm going to call this vector my vertical velocity initially in the y direction. And then if I draw this vector here, you can see that that vector is those two vectors added, right? So if I redraw my initial x velocity, I redraw my initial y velocity. Those vectors placed head to tail add to my initial velocity, which is at some angle that we usually call theta, right? So question is, how does this change our equations, you know? And for AP Physics 1, I'm pretty sure the most difficult situation we have is you have acceleration in only one of these axes, either the x or the y axis. Pretty sure that's how it works most of the time. So let's just say an object's in free fall, but it's also launched like a projectile. What you have is, see here, in the vertical direction, that's up and down, that's where your acceleration is. Your velocity graph might look something like this, right? And I can show that your displacement in the y direction is always going to be a vector relationship. So you cannot treat these as numbers. It's going to be v naught vector times t plus, this is a plus, 1/2 acceleration vector times time squared. Okay, so that's your displacement at any moment in time when something is launched in the air. But this is only my vertical displacement. My horizontal displacement is different. For a projectile, horizontal displacement, okay, so I'm going to distinguish between these two. It's actually much simpler horizontally. My sum of the forces is down, so I only have acceleration down. Therefore, my velocity in the horizontal direction will not change. Looks like this. And as you know, this area gives you your displacement. So my horizontal displacement is just going to be vxt, where v in the x direction is the vector I'm talking about above. My initial velocity is my velocity horizontally at any moment in time. So this is actually equal to v naught t because my x velocity never changes. All right. Of course, we are ignoring air resistance here. That's the only way I can justify that statement. So now, in two dimensions, we need a new vector symbol because we're not talking about delta x. We're not talking about displacement horizontally. We're not talking about our displacement vector vertically. We're talking about some displacement that has horizontal and vertical. So at any moment in time while something is in the air, after it's been launched with this initial horizontal and vertical velocity, there is a displacement. And traditionally people have been using delta r for that. Okay, so an object's launched, and from beginning to end, from its change in position is delta r. And this is a combination of delta x and delta y. And you'll notice that these vectors, delta x and delta y vector, add to delta r, right? So delta r is a combination of delta x plus delta y. Again, these are not added as numbers, they are added as vectors. Okay? And now I can just go further here. Delta r is going to be delta x, which is vt, so v in the x direction times t, right? It's going to be that vector, plus my delta y vector, which is v naught t vector added to my 1/2 acceleration vector times squared, right? Now, rules of addition apply here, where I can regroup these things, right? I really just took out the parentheses. It's one of the properties of addition. Now, what's cool is I can simplify this. Because time is a scalar, I can pull that out. If it were a vector, I don't think I would be able to do this. But Vx plus V naught. Now this is V naught y. Okay. My acceleration is down. That's acceleration in the y direction. So I could have a little y there. Plus 1/2 at squared. And the a is, of course, in the y direction. So what's nice here, let me put my vectors on there. What's really cool is if I go back to what I started at the top, right here, you'll see that at any moment in time, my horizontal and vertical velocity add as vectors to give me my velocity at any moment in time. Right? This makes a right triangle here. So not just my initial velocity horizontally and vertically add to my initial velocity that's at some angle, but at any moment in time, my horizontal and vertical velocity vectors, those component vectors, add to my velocity. This is quite powerful. This means that we can simplify this, okay? Because v naught x is the same as vx, since horizontally we didn't have any acceleration, right? So my displacement vector, not horizontal displacement, not vertical displacement, but my displacement vector in 2 dimensions is going to be like my v naught vector, because these two, my v naught x and v naught y vectors, add to v naught times t, right? Because this here is my v naught vector. So my v naught vector times t plus 1/2 a t squared. So what we've been doing all along with the area of our velocity graph when something has an acceleration, not only does this vector relationship work in 1 dimension, but it's looking like it works in 2 dimensions. And this is a situation where you have acceleration in one of those dimensions. I think APC is where you would find acceleration in 2 dimensions simultaneously. That's actually going to get more complicated to prove that one to you, but this is at least a start. And so we can use this, and I think you're going to see, as you work out some of the challenging problems, that this is an extremely powerful statement. You'll also find that velocity vector is our acceleration vector times time plus your initial velocity vector. You'll also find that this works in 2 dimensions as well, and I should prove that to you on another screencast. But these vector relationships are going to be our primary tools for solving projectile motion type problems. Okay? I hope you have a good day. Thanks for watching.